Thanks for the introduction. The goal of this study is to develop methods to control the microbubble oscillations. And this is due to the highly nonlinear and to some extent stochastic microbubble oscillations. This poses a significant problem and challenge for focused ultrasound interventions, especially in the brain, where, for example, a characteristic example, when we're trying to disrupt the blood-brain barrier, we and others have shown that stable cavitation correlates with a safe and reversible blood-brain barrier opening, whereas inertial cavitation is associated with tissue damage. So in this case, unfortunately for this case, the pressure separation to move from stable to inertial cavitation is quite small, few kilopascals. Therefore, there is a clear need for sensitive methods to infer the cavitation type and at the same time determine the required excitation pressures in the brain. So the most clinically relevant method to infer the cavitation type is using acoustic emissions. And in this case, harmonic and ultraharmonic excitations have been used to identify stable cavitation. And you can see here when we have a baseline shift, we can see broadband, as it's called, acoustic emissions. And in this case, we can say that the bubbles collapsed and there is inertial cavitation. Using the amplitude of the power spectrum, as you can see on your right-hand side, we can quantify the strength of the microbubble oscillations. And several groups, including ours, have used these acoustic emissions to control the microbubble oscillations and infer the bioeffects that are taking place, as I mentioned before. So, however, all the methods so far have relied on a single element passive cavitation detection. Therefore, they just record the acoustic emissions and then they estimate the power spectrum and try to control the microbubble activity. However, you can think and you can imagine that there are several cases where cavitation activity can happen at different places. And in case of the brain, cavitation can happen, in fact, outside of the brain. So what we were interested in asking if passive acoustic methods that can provide the spatial sensitivity can be used to achieve the required spatial as well as temporal control of cavitation activity. And a secondary but equally important question or a demonstration of this principle is whether we can control cavitation activity from a single region in the passive acoustic map while cavitation is taking place at different locations in the image. So to do so, we developed a closed-loop controller that is based on that determines the acoustic emissions level using the angular spectrum passive acoustic mapping. And this is a method that we have recently proposed and has two distinct advantages. It's extremely fast in the reconstruction time and is also frequency selective. So in this way, you can select different frequencies, and in this way, you can infer different modes of microbubble oscillations. In the data that I will show you, we use the third harmonic, the third ultraharmonic, and a region in between. We use them to determine the broadband emissions. So using the passive acoustic mapping, we determine the acoustic emissions level, and then the controller executes or determines whether we can increase the pressure if the acoustic emission threshold that we set is below the required, or decrease the step is higher. The controller also adapts and adjusts the step size depending on a predetermined trajectory that we have provided to it, and is based on cavitation threshold data, and also has embedded safety state where if we detect broadband emissions, then we take a maximum negative step. So here is the, I hope I can change that. This is a setup that we use as an in vitro study. Okay, here it is. Okay, please. So this is the control performance, where you can see around 12. The top left plot shows the harmonic emissions level, and the bottom left plot shows the output of the controller and the pressure as a function of time. The step is around, one step is equal to 1 second. And you can see, as you can see on the right-hand side where you see the passive acoustic maps, you can see that the controller can achieve robust harmonic emissions, and at the same time, they could have a complete absence of broadband emissions and therefore inertial cavitation. And this was what we tried to test the control under these conditions. So having demonstrated that we are able to control in real time using passive acoustic mapping the cavitation type, then we move to ask the second question, is if we have cavitation occurring at the same time in two different locations, can we select the region of interest and control the cavitation only in that region of interest? And as you can see from the bottom left plot here, where it says region 1, the region 1 is a region of the tube with vessels that is at the focal region of the focus ultrasound, and region 2 is at the periphery of the focus ultrasound. So when we control for the region 1, you can see that the controller required much lower pressure to achieve a predetermined level of cavitation activity, and whereas when we try to control for the right region, you can see that the higher pressure levels that were required to achieve that threshold values that we provide, suggesting that we can indeed control cavitation activity on a very well-defined region using passive acoustic mapping. And then you can see the temperature, the rise of the controller is of the order of 10 seconds, but this highly depends on the step size that we use. I think I would like to say one additional advantage of using passive acoustic mapping for determining the different regions is that it provides much clearer definition and onset of the different harmonic components, and therefore it provides much better definition when we have the onset of harmonics, ultraharmonics, and broadband emission, and better definition of stable and inertial cavitation regimes. And this, we think, this sensitivity can be used to expand the safety margin of current treatments, and at the same time increase the treatment efficacy and potentially reproducibility of passive acoustic, of therapeutic interventions, in addition to providing spatial localization and promotion of cavitation activity. So to conclude, the controller based on the angular spectrum method can provide really good temporal resolution for most of the cases that we're interested in, and provides also has also the location specificity. And we use the harmonics, ultraharmonics, and broadband emission at the same time to allow for reproducible control. And now we're moving forward in testing this controller during in vivo conditions. With that, I would like to thank you, and I would like to thank the NIH for supporting this grant, this work. Thanks.
Are there any questions from the audience? Okay, go ahead.
Yeah, I was wondering, when you want to go in vivo, you will have a very, very variant plasma concentration of bubbles. How will this actually interact with your feedback controller?
So what the bubbles, you mean?
If you inject a bolus
Yeah.
of microbubbles, you have a very, very strong concentration change
Yeah.
in a very short time.
Sure.
And how will this interact or impair your control algorithm?
Sure. With the bolus, we need to make more adaptive the controller so it can account on the bolus, but at the same time, we don't have to inject bolus. We can infuse bubbles, as we have shown in several experiments with non-human primates, where you use a bolus infusion, and we're able to have relatively flat cavitation activity throughout the experiment. So this could be, I would recommend that kind of approach for using controllers.
Any other questions from the audience?
What's the pulse duration and the corresponding spatial resolution you can get?
Sorry?
The spatial resolution.
Spatial resolution.
Yeah.
Spatial resolution determined by the diffraction limit in this case, and it depends on the frequency that you are using. For us, we use about 2 megahertz, so it's of the order like 1 millimeter in the transverse direction, and a couple of few millimeters in the axial direction.
Okay, one last question.
Sorry, it may be a naive question, but if you go in vivo and image through the skull, if you use 2 megahertz frequency, how do you do with absorption and aberrations? Like your spatial resolution wouldn't be like without skull, and 2 megahertz is completely absorbed, probably.
Sure, I wouldn't call this a naive question. That's a really good question, I would say. So there are like 2 things. One is like experimental limitations. We just decided to use this because it was overlapping with the bandwidth of imaging probe that we had. But the most important component is using the harmonics, which is based on the excitation frequency. So if we go for example, in transcranial system and we use 220, we should definitely be able to record with a third harmonic, which is going to be around 660 kilohertz, and we have shown that. So that was like one of like demonstrating the proof of principle that the controller works. And the second question, which is with regard to aberration corrections, we have already solved the problem of using angular spectrum method in arbitrary media with arbitrary density variation. So I don't think that will be a problem as well. I didn't present that here, but we will present that. We'll publish that work soon. Thanks.
Okay, thank you.